Assalamualaikum and salam sejahtera. This is MKL1273 VLSI Design Automation class. I am Dr. Nasir Sheikh Hussain. Today's topic is global and detailed placement. I'm not going to explain all the slides. Please read the slides that I skip on your own. As we learned last time, floor plan placement is rather similar. The only thing is, besides placement, floor plan, placement also involves some other considerations. For example, the wire length after we do the placement and the routability of the wires. This is an example problem. We want to do placement for this bunch of gates. This is one solution. So you can see that not only we do the floor plan, the location for each block, but we also need to consider the wire, the interconnect between all the blocks. We can do this either in 1D like this or in 2D, X and Y direction. This placement consists of two phases. We do global placement first, followed by detailed placement. As I mentioned, rather than wire length, we may consider other optimization objectives. For example, number of cut nets, wire congestion, and signal delay. We want to make sure that although we perhaps manage to do the routing of the wires, for critical nets, we want to make sure that the delay for that critical net is within a stipulated delay. This is an example of good placement here and rather bad placement. You can see here that the wires are rather congested, and we may not be able to route all the wires when we do detailed placement and routing later on. So this is much cleaner, and chances are we will manage to do all the routing successfully later on. There are several estimation for wire length. HPWL, half perimeter wire length, is very popular. In this example, how do we do it? We have these 4 nodes. We draw a rectangle outlining the outermost node, and the wire length is estimated to be half of the perimeter. In this case, half of the perimeter is 4 plus 5, so estimated wire length is 9. There are other estimations. Click length 14.5, chain length 12, star length 15. So not only these 4, we have other methods. There are 4 more methods here. The last 3 is very accurate estimation of the actual wire length, which is 10. RSMT, rectilinear Steiner minimum tree, is very popular. However, this is rather complicated algorithm. There is a simpler algorithm, which is rectilinear minimum spanning tree, RMST. So according to RMST, the length is 11, so it is not as accurate. but RMST is much simpler. The algorithm is much simpler compared to RSMT. But remember, RSMT is rather accurate. However, as I mentioned, the easiest, and that's the reason why HPWL is popular, is HPWL can estimate quite accurately. In this example, according to HPWL, the length is 9, but the actual length according to RSMT is 10. So only 10% error, which is acceptable, because the algorithm for HPWL is very simple. So in conclusion, HPWL is very popular. So many algorithms use HPWL to estimate the wire length. It is because it is faster, an order of magnitude, meaning 10 times faster than RSMT. And then extensive study has been made, and it was found that for most for actual circuits, HPWL, the error for HPWL compared to the actual wire length is about 8%, which is quite good. We can also give a weight to each net. In this case, in this example, we have 3 nets, N1, N2, and N3. So N1, there is a weight of 2, N2 has weight of 4, and N3 weight of 1. So in this case, what is the actual length for N1? 1, 2, 3, 4, 5, 6, 7. The actual length for N1 is 7. But because it has weight of 2, so we consider the length for N1 is 7 times 2, 14. Similarly, for net N2, the actual length is only 4. 1, 2, 3, 4. But because it has weight of 4, the total wire length we consider it to be 16. 4 times 4. And for this one, length is 3, weight is 1, so total wire length is 3. So in this example, the total wire length is, including the weight, is this, which is 33. So how do we try to minimize the wire length? One of the things that we can minimize is to reduce number of cuts between blocks. If we don't have too many long wires from one block that needs to be connected from one block to another block, if we reduce that, that means most of the wires are local wires. That is, wires only within each floor plan. So you can see that if we have that case, so the wire length can be minimized. So how do we measure the number of cuts so that the algorithm will try to minimize? So we can split into two. One is vertical cuts, and the other one, of course, is horizontal cuts. So the total number of cuts is summation of all the vertical cuts and all the horizontal cuts. In this example, the same nets, N1, N2, and N3. If we split our floor plan, our chip area, into 9 blocks, 1, 2, 3, 4, 5, 6, 7, 8, 9, by having 2 vertical cuts, V1 and V2, and 2 horizontal cuts H1 and H2. As before, we have the same 3 nets, N1, N2, and 3. So in this case, there are 1 cut for V1. We have 2 cuts for V2. We have 3 cuts for H1, 1, 2, 3, and we have 2 cuts for H2. So this is the definitions. Another definition is cut size. So for vertical cuts, we have 2 cuts. The cut size is determined by the cut which is the larger one. In this case, we have 1 cut here and 2 cuts here. So for vertical cut size, it is 2. Similarly, for horizontal cuts, here we have only 2 cuts, and here we have 3 cuts, 1, 2, 3. So for cut size for horizontal is equal to 3. For routing congestion, first of all, there are 2 types of routing. One is switch box routing with a structure like this, and channel routing. So you can see that for channel routing, the routing is only one dimensional. I mean, only horizontally. But for switch box, we may have horizontal routing and also vertical routing. How do we measure routing congestion? So we measure it by defining this parameter phi p, wire density, which is given by this equation, eta p divided by sigma p. Eta is estimated number of nets that cross HE, and sigma is maximum number of nets that can cross E. If sigma greater than 1, then it indicates that the wire not all wires may be routable. The wire density, capital P, designated by capital sigma, is the maximum among the wire densities. So we have many edges. The one that has the largest among the edges, so that is the limit. So we call it wire density P. For what it indicates is if wire density P less than 1, it indicates that most likely all the wires will be successfully routed. In this example, assuming we divide the chip area into 9 areas, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we define this is horizontal cut H1, this is horizontal cut H2, H3, and so on. And for vertical, we assume that this is vertical cut V1 and this is vertical cut V2. So how do we measure wire congestion or wire density? Just for each cut, count the number of wires that goes through each cut. So in this case, for cut H1, So we have only one wire that needs to be routed through H1 cut. Similarly, for H2, we for this implementation we require two, one here and another one here. For H6, for example, this is H6. There is no wire crossing H6. For V1, this is V1. There is one wire that crosses it. And as you can see, for V5, here, V5, there are two wires. So the maximum for all 9 cuts, 12 cuts, 6 horizontal cuts and 6 vertical cuts, H1 to H6, V1 to V6, the maximum is 2, which is required by H2, 1 and 2, and for V5, 1 and 2. Assuming that the capacity for each cut is 3, this is we assume it is 3. So what is wire density? So wire density is 2/3. So because we assume that each cut can accommodate 3 wires, so we can estimate that we have no problem routing this wire. All wires should be routable. Again, this is an example. Another issue regarding placement is the signal timing. After we do the placement, we want to make sure that the delay is not too large. So there are two terms here. One is actual arrival time, and the other one is required arrival time, RAT. Actual arrival time is the signal delay from the clock transition until it arrives at node V. The signal arrives at node V. For example, node V is the input of the flip-flop. So when is the time, the signal from the beginning of clock transition until the signal stabilizes at the D input of the flip-flop. So the delay is, we call it actual arrival time. So as long as what we want is when we do our placement and routing, we want this AAT to be lower than required arrival time. For a global placement algorithm, there are many algorithms which is loosely classified into partitioning based algorithms, analytic techniques, and stochastic algorithms. You are familiar with stochastic algorithm. Usually it will involve simulated annealing. For partitioning based algorithm, we subdivided the problem into smaller subnet lists and subregions. After it becomes small enough, then we do partitioning, for example KL or FM. For analytic techniques, there are several algorithms. One of them is force-directed placement, quadratic placement and force-directed placement, which we will discuss further on later. So this is some illustrations of the categories of global placement. For partitioning based, as I mentioned, we partitioned one big problem into smaller partitions and then we solve for each partition. For quadratic placement, something like we put all our solutions initially, some initial solution, and then the algorithm will relax the placement and it will fill in all the allocated regions. For force directed, similar to quadratic, we place something and then the algorithm will try to group relevant blocks closer or farther as necessary. And as you know, for simulated annealing, it is stochastic. It depends on our random choices. For min-cut placement, as I mentioned, we subdivided the problem into smaller sub-regions, smaller subnetlist and sub-regions, and then we use KL or FM to cut each small regions to minimize the number of cut nets. For min-cut placement, we have several ways of subdividing one big region into smaller regions. We can have alternating cut line directions. What it means is, first we cut in horizontal direction to split into two areas, above and below. And then now we cut vertically to split into 4 regions. And then after cut vertically, we cut horizontally. So we cut here, we cut here, we cut here, we cut here. And then the last cut is now vertically. So we cut here, 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 like that. So in the end, we have 16 regions. Similarly, we can what is called repeating cut line directions. So we keep cutting in the same direction. So for example, in this case, we cut horizontally once, then we cut horizontally again here and here. So now we have 4 regions, 1, 2, 3, 4. And then to split further, we are going to cut vertically. So we cut here 3A, 3B, 3C, 3D, and then we cut here 1, 2, 3, 4, 1, 2, 3, 4. So you can see that we cut in the same directions until we are done. So again, we have split now into 16 regions, smaller regions. This is the algorithm for min-cut placement. I'm not going to go through. This is a rough idea of the implementation for min-cut placement, which, as I mentioned previously. As an example, we are required to make a placement for this circuit. We are allocated 4x2 regions. So use KL algorithm for min-cut placement using alternative cut line directions. That means we cut in one direction, and then for the second cut we change the direction. In this case, we are going to use vertical cut first, and then we are going to use horizontal cut. Since we are allocated 8 slots and we have only 6 gates, so we are going to introduce 2 dummy gates. So As example here, these are the two dummy gates that we have to introduce because we, as I mentioned, allocated 8 placement regions. So randomly we cut, as I mentioned, we cut vertically first to split into half. So randomly we have 1, 2, 3 on the left partition and 4, 5, 6 on the right partition. So graphically represented like this. And we will be using KL algorithm. So as I mentioned in module 1, KL algorithm. So after we solve this using KL algorithm, this is the solution. So you can see that instead of 3 cuts, KL algorithm solve the partition, and in the end we have only 1 cut. So now we have split the circuits into left partition containing gates 1 to 4 and right partitions containing gate 3, 5, 6. So these are the same diagram here. So after we have do the initial vertical cut, now we have to split on the left partition and the right partition to split into 2 regions. So because we are going to the first cut was vertical, now the second cut is horizontal. So now we are going to split the left partition using horizontal partition. So randomly we cut horizontally to split cells 1, 4 on top and 2 and dummy cell 0 at the bottom. Similarly for the right partition, 3, 5 on top and 0, 6 at the bottom. So this is arbitrary cut, and then we use KL algorithm to solve the optimized partitioning. In this case, because well, the example is very simple algorithm, very simple example. Our initial cut actually correspond to the optimized cut. The KL algorithm cannot improve it further. You can see that definitely cannot be improved further. Similarly for the right partition. So so we need the next one is we need to cut again because, for example, here we have 2 cells. So we are going to split into individual cell location. So the next cut is vertical. So finally we are going to cut like that to split 3 and 5, and here to split 1 and 4 and 2 and 0. So we split 1 and 4, 0 and 2. Here 3 and 5 and 6 and 0. So this is the final solution, and this is the actual placement corresponding to our original circuit. You may wonder, after we do the final partitioning, for example 1, 4, 2, 0. So why do we in this case 1, 4, 0, 2 instead of 2, 0? So you can see here why, because when we put 2 here, then 2 can be connected to 4 more easily. So that's why we put 2 and the dummy cell here rather than put 2 and then dummy cell here, as may be indicated by this one when we split vertically. Similarly, it is not that obvious that when we split like that, is it 0, 6 or 6, 0? So how do we solve this? Actually, this min cut placement, there is a supplemental algorithm called the terminal propagation technique. This terminal propagation technique solves the dilemma that we have. To illustrate with slightly more complicated example, so in this case, we have 1, 2, 4, 3 like this. So we have decided to split 1 into displacement, 2 into displacement, but we haven't decided yet when we are going to split vertically to separate 3 and 4. Should it be 3, 4 or 4, 3? How do we decide the proper placement? So I'm not going to highlight the detail. All I'm saying is it can be solved using terminal propagation by introducing this dummy nodes in hypergraph, which I'm not going to go through. Okay, so this terminal propagation sub-algorithm will indicate to us how to do the final placement. In this case, the solution is we should put 4 on top and 3 at the bottom, like this. It will result for this example with like this. So very simple interconnect. If we put 3 and 4 like this, so 3 here, 4 like this, so you can see that in the end we have quite substantial wire in order to finish our connection. So very long wire here instead of very short wire, and similarly output here go to the input, very long wire, instead of output go to the input, very short distance. So there is an algorithm called terminal propagation algorithm to solve the proper placement, but I'm not going to go through this exact algorithm. In summary, min cut placement, it is reasonably fast. It is hierarchical strategy, so it is applicable to large circuits. Remember, we subdivided very large problem into smaller sub problems. The disadvantages of min cut placement is it is randomized chaotic algorithms, because as I mentioned, in previous example we use KL algorithm. So we put initial partitioning randomly, then we use KL algorithm to solve the proper partitioning. So as you know, the final output of KL algorithm depends on the initial partitioning. Another disadvantage is when we optimize one cut line for that particular partition, it may result in routing congestion elsewhere. By repositioning cells between the allocated placement regions, we may disturb the routing elsewhere. As I mentioned earlier, there are several other algorithms. I just explained min cut algorithm. The next one is quadratic placement. In quadratic placement, we use this called objective function LP given by this. What it does, if you look here, for example, we have 4 cells, n equal to 4. So measure the distance between cell 1 to cell 2, cell 1 to cell 3, cell 1 to cell 4, which is given by this equation, and then cell 2 to cell 3, cell 2 to cell 4, total them together, and then the distance between cell 3 and cell 4, finally cell 3 and cell 4. So total them all those distances, solve the quadratic equations to find the proper placement, so that the distances between cell 1, cell 2, cell 3, cell 4 are minimized. So how do we do that? Okay, so we have this objective function. So differentiate partial differentiation and equate the partial differentiation to 0. With that, we can find the proper locations for all 4 cells in this example. This problem is similar to least mean square method, root mean square method, which is graphically shown here. That optimization function, that L optimization function, will have a minimum here only at one solution space. That means there is only one placement where the distances, in my example previously, we have 4 cells. There is only one placement where the distances between N1, cell 1, cell 2, cell 3, cell 4 is minimum. Back to this objective function LP, we can split this function into x dimension only and y dimension only. To make the illustration simpler, assume Cij is 1. Okay, Cij is connection cost between cells I and j, because the algorithm is quite flexible. For example, between cell 1 and cell 2, we can make this cost cell 1 and cell 2 to be huge. If we do that, what we are telling the algorithm is, please do not separate cell 1 and cell 2. Because if you split, then the distance between C1 and C2 will be huge. So forget about that complexity. So we assume there is no preference between cell 1, cell 2, cell 1, cell 3, cell 1, cell 4. So we can assume that all Cij is equal to 1. So then we eliminate Cij. So for x dimension, for 4 cells, then we have this equation, summation of x1 minus x2 squared, x1 minus x3 squared, x1 minus x4 squared, plus x2 minus x3 squared, x2 minus x4 squared, x3 minus x4 squared. So we have those how many 7 or 6 summations. So differentiate that, equate to 0, so we can find the x locations for the 4 cells. Similarly, in y direction, for 4 cells, we have y1 minus y2, y1 minus y3, y1 minus y4, y2 minus y3, y2 minus y4, y3 minus y4 squared, and so on. Okay, so differentiate, equate to 0, we can find the y locations. More specifically, we can solve it. Okay, so in the end, we have the solution in the form of ax minus bx equal to 0 for x direction, and ay minus by equal, and equate that to 0. So we can solve this to obtain x and y coordinates. This solution consists of system of linear equations, so we can solve to find x and y locations. This problem is rather similar to the mechanical analogy mesh spring system. How do we separate the springs so that the total force among these 3 strings is minimized? similar to this mechanical analogy. One problem that this algorithm faces is the solution has the tendency to stick very close to each other. So, for example, in the 4 cells, everybody wants to be very close to each other. So, which is not practical, because each gate has a finite area. So, the next cell must be outside of the boundary of the first cell. But the solution may give the location for the second cell inside the area for the first cell. So they tend to overlap. As illustrated here, so many cells wants to be at locations very close to each other. So the algorithm needs other mechanism to make sure no overlap is allowed. So there is built-in algorithm so that the cells are spread out. There are several techniques, repulsion forces, geometric sorting, and scaling. There are several techniques which we are not going to go through in detail for all of them. This algorithm has the following advantages. It captures placement problem concisely in mathematical terms. Number 2, efficient algorithm from existing numerical analysis and software are available to solve the linear equations, the partial differential equations, to find the location for x and y coordinates. Existing numerical software are available. The algorithm can be applied for large circuits without netlist clustering, with the help of spreading algorithm, and it is stable. Small changes in the input do not lead to large changes in the output. The disadvantages, one big disadvantage is connections to fixed objects are necessary. So the algorithm requires I/O pins for fixed macros, etc. It needs artificial additional inputs rather than the actual net list for the algorithm to work.